And let's proceed with our second lecture today from Stoyan Nikolov, Chief Software Architect and co-founder of Coherent Labs. They built high-performance HTML renderers and UI system for AAA games. If you don't know, I don't know. That means those million-dollar budget blockbusters, which means that products that Stoyan has designed are deployed in more than 100 million devices worldwide. And what is most important, he uses exclusively modern C++ as a key factor for performance and ultimate success of that of the software. And something tells me you have quite a few people who are compatible with that thinking in this audience. So Stoyan is genuinely frustrated by applications which run slow and additionally consume tons of RAM. And he hopes that, quote, "we can bring back some of the lost craft of creating more with less." But when I asked him what is his real motivation to giving this speech, he modestly said, "I believe it's an interesting topic. I'm convinced already, but let's find out." This is Data-Oriented Design in Practice by Stoyan Nikolov.
Thank you. Thank you, Lucas, for the kind words. So, hello, everybody. I'm Stoyan, and today we'll be talking about data-oriented design, and especially how it can be applied in real-world systems, not the, let's say, theoretical stuff that we often see. So a couple of more words about me and why I decided to do this talk. So I've been in the video games industry for the last around 10 years. And I worked on games, but now I'm working more on only on the technology of games. So we create at a company called Coherent Labs, where I work as a software architect. We create software for game developers. And obviously, we have a very demanding user base, a very demanding crowd. Are there any game developers here in the audience? I don't see many hands. I don't see any. I see one hand. Okay, we won't be talking about games, so it's great. So in the last 6.5 years, something like that, I've been working on technologies based on HTML rendering. So we have Chromium that we've worked on, we have WebKit, and now we have our own Hummingbird technology, which is an in-house HTML renderer in-game browser. And I don't know how familiar you are, but Chromium is the open source project at the core of Chrome. And WebKit is a HTML renderer that Chromium's own core, which is called Blink, was forked from. And WebKit is actually at the base of Safari. So if you use Chrome, if you use Opera, if you use Safari, and a bunch of other more or less known browser, you're running some versions of the code that I'll be showing very shortly. So while working on some of our projects that were based on Chromium and WebKit, as you know, in games, performance is super important. We did a lot of optimizations. We did our own rendering and so on. However, while working on this, with every improvement that we made, with every new version, we still saw that we can do so much better for the problems that we were solving, but that there was something that was stopping us, and it was the core architecture of how WebKit, for instance, is designed and how it is done. You cannot really optimize to the maximum of your possibilities if you don't change something in the architecture. You hit that boundary. So we were at that boundary, and I gathered with my co-founders, and although we had worked a lot on this, we decided to do the only sensible thing. And as we are developers, the only sensible thing is to start from scratch, of course, to begin from the beginning. And we decided to build our own HTML renderer. And for that, we decided to employ data-oriented design. So a lot has been written, especially in games, about data-oriented design. We had some experience because we had built our, for instance, rendering engine with data-oriented design, but we didn't have. We weren't sure, actually, if it will work for a project of the scale of an HTML renderer, of something that has to implement such a complex design and standard as HTML rendering. Unfortunately, the design itself of the standard for HTML and CSS is very object-oriented-y. So today I'll show you quickly how it went. So I have a very, very brief demo. It's a video I recorded on my phone, but it's visible. Okay, it's a very simple web page, basically, with 3,000 animations. On the right side, you see it running on my phone with Chrome, and on the so actually on your left, on your left, it's Chrome. On the right, it's Hummingbird. You see that there is a performance difference, right? One is running at around 5 to 7 frames. The other is running on a smooth 60. So we did something right. At least the performance is there. And let's see how we got there. Okay, the agenda for today will be to look at the basic issue of object-oriented programming. I guess everybody knows what object-oriented programming is. Everybody has worked with it. Then we'll look at the basics of data-oriented design. I won't go into too much detail. There are awesome talks on the internet, and I have links at the end that you can watch for an overview. But the most important part of this talk will be looking at the real-world problem and how it is designed with object-oriented approaches and how it is designed with data-oriented approaches. And then we can analyze and see what results you can get with one or the other, or some combination probably. So object-oriented programming is a concept that marries data with the operations that you apply on them. This is the basic premise that it gives you. It has other aspects, but this is the most core thing usually. So it's not often, however, a happy marriage, because with the evolution of your software, even if you start with a very clean design, you very often end up with these logical large black boxes of objects. So if we have an example from a game, let's say that we have an entity that is our enemy, and that enemy might be an object, but it has different data inside it. It all logically belongs to it, like it's a physics object, it's AI, and so on. So if you put it in classical object-oriented design, you'll have them bunched together in this object, but they will be used in vastly different contexts within your program. You'll be using it for physics, you'll be using it for AI, you'll be using it for rendering, and so on. And also, when you end up with these large black boxes of objects, you also have this hidden state all over the place. So you have all these booleans. In this case, this object has to do this. In this other case, it has to do something else. And we'll see how that impacts, finally, the different aspects, different software architectural quality attributes we're interested in, at least in this talk. So this is performance, scalability, modifiability, and testability. And of course, your mileage may vary. There are good examples of object-oriented programming code bases, but even very successful ones suffer from this problem, especially in the long run. So data-oriented design takes a bit of a different approach. It's more of a mental model, but on this slide, on the lower part, you can see a typical example of how you would organize your data in object-oriented programming. You have two logical entities. They have their fields, whatever they are, and you bunch them together because they, in a sense, belong together. You know, the classical example, a car is a car, it has tires and so on, but there is no car in your computer, so this is an artificial example. And data-oriented design tries to forget about this real world that object-oriented programming tries to model, and it tries to work as to embrace how the machine will actually execute your code and transform your data. So if we have system alpha and system beta, you can bunch together the data that they need in different structures and pass them where they are needed. And you can build this sort of pipeline in your code where the results from one computation generate new data that is passed along to the other computations down the line until the result that you want to get. So the gist of data-oriented design, it's the separation actually of data from logic. You try to embrace the data, you try to reorganize it the way that the machine will most well use it. So you're no longer programming for this abstract machine that doesn't exist. You think about how the actual machine, the actual hardware will work, and try to design your program in the way that it will work best. So you embrace, for instance, that CPUs have caches. This is a fact of life. This is an extremely important fact for performance. So you shouldn't hide it. You should embrace it. We try to reorganize then the data according to their usage so that we make the best of those caches. And data-oriented design is one of those areas that it promotes deep domain knowledge. We'll see how, but it's very difficult for you to really design the software well in this manner if you don't know the problem you're trying to solve very well. So the first thing is find the problem you're solving and then design your code, not the other way around. And first think about the data and then the code. The data is the most important thing. It's not the code. It's not how you express it. I have references at the end. There are awesome talks on this, so you can check it out. So if we talk about the differences between those two, I think that good object-oriented programming shares a lot of the traits of data-oriented design, but this good object-oriented programming is hard to find for various reasons, for misconceptions, for the evolution of software, and actually, even if you don't want to embrace data-oriented design full-on, just thinking about your code and your software in this matter will probably make your other designs better as well. And there's a good quote actually that I like from Robert Martin, who's actually a very object-oriented guy, and this is a book where his examples are in Java, where you actually cannot do half the bunch of the stuff that I'm going to show you. But he says that mature programmers knows that the idea that everything is an object is a myth, and sometimes you really do need simple data structures with procedures operating on them. So it's a good quote to keep in mind when you design your software, especially even in languages that don't have all the facilities that C++ has to go really low level. So data-oriented design has been mostly demonstrated in games. I won't be demonstrating it in games. I'll be demonstrating it in a different system, as an HTML renderer and a specific system within that HTML renderer that we have time to look at. So the system at hand will be the system of CSS animations. I don't know how many people of you are familiar with HTML, CSS, and so on. A deep knowledge is not required. CSS animations are just a way for designers or web developers to create animations within their pages. And here I have, to illustrate that idea, a very simple example. Okay, when I imagine this is a game, when I click on the card, I execute two animations basically. On the left side, the card is flipped and some text comes in. So this is done with CSS animations. It is a way to add dynamism to the elements within a page. And the cool stuff is that you can actually animate different types of properties. So you can move your elements, you can change the opacity, you can make them show or hide, and so on. So the animation definition is very simple. It's a declarative syntax, and it allows you to have keyframes. Again, everybody who's done any animation knows what this is. And you can tell that you want your element to have that animation. It has a name, which are the keyframes. It has a duration and a bunch of other properties. We're not interested in them. These are the most important ones. We already see that there are some important considerations for us when we design these systems and make this system and make it work. The first one is that we can actually animate different types of properties. So you can animate a color, matrix, a simple number, and so on. And you have to deal with this when you implement the system. And then these definitions are not cast in stone. While the application is running, the user can modify it. So there is an API that allows the user to change for instance, the duration of the animation or some keyframe. So you have to take that into account as well. So let's try to design this system with object-oriented programming. How can we implement this? We'll be looking at a concrete example from Chromium. This is taken from Chromium 66, which is a fairly recent version. Chromium actually has two animation systems. We'll be looking at just one of them. The other has a very similar design. And if you haven't worked or studied Chrome's code, I very much invite you to do so. It's an amazing piece of software. It's very large, but done by some of the best engineers in the industry. And there's a lot to learn there. And they use in this system some classic, although in some ways dated type of object-oriented programming. Although this standard is fairly new, Chromium's code base is fairly old, and this particular system uses not the best object-oriented programming, at least the textbook one that you know. So let's try and see how it works. Obviously, we go into the code base, and the first thing that we do is look for a class called animation. And there is one, so we're on the right path. It's final, which is good. We know that it won't be inherited by anything. But we already see that it's a bit of a dated code base in the sense that it inherits six other classes. And actually, here's the inheritance hierarchy. You don't have to read the details. It's very complicated. And many of those are not pure interfaces. They are classes with data and methods. And unfortunately, a lot of code bases, with their evolution and with the addition of new constraints or new requirements, end up with a hierarchy similar to this, even though it might have not started like this. So we saw the hierarchy. It's very complicated. So let's directly go to the code and see how one specific part of that works. And we'll be looking at the most important part, the animation part. So the thing that happens every frame and modifies the properties so that something moves on your screen. And we look for the flow. It's fairly what you would expect. There's a document timeline object that has a method called service animations. So pretty clear there. There's a vector, so an array of animations needing update. Again, very clear. And on each one of those, they call a method called update, and they take the time inside. This is good. It's what you would expect, but we already see something peculiar, and it's that they're not iterating over the vector of the animations that need update. They're actually copying that and iterating over the other one. And the reason for this is that apparently there are code paths that will lead during the animation running to the deletion of that pointer within the original vector. So it's already difficult for us as people that are reading the code or people that are going to maintain that code or work upon it to reason about the cases when that vector will be modified. And that has some interesting effects down the line. So next up, we go into this update method. Okay, it's what you would expect. There's a timing update reason and so on. But the very first line should ring a red bell in your mind. It's if there is no timeline, which is some kind of pointer, you return false. And it means that in this vector of animations that are apparently needing update, there are actually animations that don't need update. They just have to, they don't do anything. And if we were thinking in the framework of this abstract machine, this is an operation that costs pretty much nothing. But as we are in the real world, this operation is actually very costly. Because each of these animations they are pointers, they are allocated on the heap. So just for us to read that pointer, that timeline is null, we're actually probably incurring a cache miss on our processor. And that's just to see that we don't have to do nothing and return. And this is a very significant performance penalty. Then we might have branch mispredictions because the CPU tries to guess all the time where your branches will be going. And if we have, let's say, 50-50 animations that have to run, animations that don't have to run, the branch predictor will be put off. It cannot really tell which branch to take all the time. And we see the same thing a couple of lines down with this if content. So we'll be skipping a bit on I won't go into every call stack because it's a very deep one. I'll be just looking at the highlights. And next up on this content, we actually delegate the calculation of the animation to another object, which is called, declared a member, and it's of type animation effect read only. And a member, you can think about it as a type of a smart shared pointer. So Chromium does garbage collection in C++. That's how they annotate their types, but you can think of it as a shared pointer. So we are probably getting another cache miss because this is again an object allocated somewhere on the heap. Next up, we are going to update the time and the values of our animations. But before we do that, we see that if there is an event delegate, we'll be calling an event condition. So in some cases, the animations have to propagate some change or notify someone that something is changing. And this is a very common pattern in object-oriented programming. You delegate and you say something that's happening to someone else. But this again has significant repercussions, because if, for instance, that event delegate calls JavaScript, we'll have a very high performance penalty on this call. We don't know what's going on there. But if we call JavaScript, it will evict all the data that we have in our caches, because we will have to load a bunch of other data that is called. It will have to do something on that and then return to our context of our animations and reload all the data that we had again. So it's a performance penalty. Then we have the fact that we're coupling our systems. Our animation system now knows about the events and the event delegation and so on. So not that great. Next up comes an interesting problem. I mentioned in the beginning that our system has to handle different C++ types that can be interpolated, basically. We have the keyframes, we have time, so we have to get an interpolation between those two for the time that we have. It can be a number, it can be a color, it can be a matrix, it can be a bunch of stuff. So, but we still want to have a nice interface. So how can we do that in C++? There's a simple way. Anyone? How was it? Yes, exactly, with a virtual. So an abstract class. There is an abstract class, an interface called interpolation, that has a virtual method called interpolate, and you can implement that for any type that you want. It works, obviously. However, it's a way of doing dynamic type erasure in C++. And it has some effects. It incurs a cache miss, because you have to allocate that class on the heap, and you have to call that virtual method. And it has this effect on performance. Next up, we have calculated this new value, and we want to apply this new value to the elements that are changing. So they have a member, called target, and this is the element that will be animating. It has a method called setNeedsAnimationStyleRecalc. It will be us that will be setting the new values on that target. And now we have again a coupling between the systems, because our animation system knows about the styling and it knows about these elements. And it's some unclear lifetime semantics, because this is again a type of shared pointer. So what happens if the element gets destroyed? Or will the animation keep it alive? It's difficult to know from this code. And as the element for our animation system is a black box, we don't and shouldn't care, according to object-oriented programming, what this setNeedsAnimationStyleRecalc method does. We don't care, but it has a significant effect on the performance and our system. And this is a peculiarity of how Chromium does its restyling, but it applies to any system where you call some method and you don't know what it does. In this case, it has a big performance penalty. For the first reason is that it has to call this element, which is again somewhere on the heap, so we get a cache miss there. But what's worse, if we go into the implementation, actually it calls this set needs star recall to every parent within the document object model of our page. It's just an implementation detail for them, but at the same time it has a significant effect on us because it will incur multiple cache misses, and it will define in a very concrete way the performance profile of our animation system. So to recap, we used more than 6 non-trivial classes. They used smart pointers for the systems. We got some coupling between the systems because of that. And we got some unclear lifetime semantics on some of the stuff. So let's try another approach. Let's try data-oriented design and rethink this system in that way. The first thing is forget everything we saw. Let's get back to the drawing board and start thinking about the most usual operation that happens in our system. Obviously, this is the tick, the update. It happens every frame. Every frame we have to move a bit our animation. We have to calculate a new value. We have other operations, adding, removing, stopping, and so on animations, but they happen an order of magnitude less often than the ticking. So we want to design our system around that operation. We have to also design and decide the input and output of our system. The input is very clear. It's the definition of the animation so that we know what we have to do, and it's time. And the output, again, is clear. We know exactly what we need and what the other systems will need. So we need a list of the properties that have changed. For instance, the color, the position, and so on. We need the new values of those properties, and we need the elements that those properties have to be applied on. But it's not our job to apply those properties to them. And we also want to use another core principle of data-oriented design. We want to design around the most happening case, the most often case, which is that we have many animations. We want to optimize because we know we'll be doing many animations, not just one. So let's create a class called an animation controller. Very, very simple. It has a bunch of active animation states. It's the data for each animation. It takes as input time. It has generated from the definitions those states, and it outputs exactly what we need. So a bunch of properties that have changed, their new values, and a bunch of pointers that know the values that they will have to use. And here, the elements are just dumb pointers. The animation system does not know what this element is. It does not care. So there is no coupling with the other styling system. And down the line, the other systems in our pipeline, our styling or our event notification system, can just take this output data, inspect it, and decide what to do with it. So how do we define this animation state? The first thing is we go flat. We remove the methods. It's just a simple C++ struct. It is conceptually split into 2 parts. The upper part, which I call the runtime part, is the current state of the animation. So when it started, how many iterations have passed, and so on. The second part in this slide is actually the animation definition. It is how long the animation has to be, what is the fill mode, and so on, what's the direction, if it has to go forward or backwards, and so on. And there are 2 ways to actually have the definition and implement this. On the left side, you see something similar to what the Chromium code was doing. So you have the different states, and you have the definitions as pointers in them, and you can point to them and use that data. And this has some pros. It allows you to save some memory, because a lot of the definitions will be actually the same for all the animations that are running. On the right side, you have another approach where the definitions are copied or cloned into each state. So on the left side, you have, however, some issues. First, you might have cache misses depending on your workload. Second, when you have to modify an animation, and we said that this is possible because the user can do it and it's a requirement for our system, you have to employ some type of copy on write semantic. So if that definition is used by multiple animations and you want to just change one, you have to clone it and modify just the clone. You cannot, otherwise you change other stuff that you don't have to do. On the right side, this is simpler because as we have cloned it in the beginning, we just modify the state and it will not affect anything else. And we have gone for the right side for different reasons. One is that it simplifies code. The second is that empirically we have discovered that it works better for our workloads. But your mileage may vary. There are different approaches to the same problem. Okay. The animation state, however, had no keyframes. I hope you noticed that. There was no information there about the different keyframes that we have. So the different types of properties that we're modifying, the colors, numbers, matrices, and so on. So how we do that without relying to virtuals and to interfaces and to dynamic allocations? Well, C++ has a way to do it. It's a type of static type erasure. You can do it with templates. So let's try it. We templatize a class that inherits our animation state, and it's templated by the type of the keyframe. Great, now in code it looks fine. But every state that we have has a different size in C++. So we cannot put it in the same, we cannot put all those in the same array. I'm sorry, I have a bit of a cold, so my voice is leaving me at some moments. So how do we deal with this? Well, there is an insight from our domain knowledge, and it is that we know at compile time every type that we want to interpolate. We know which one of those we have. So we can do a very simple thing. We can have arrays for each of these types. We can generate those at compile time, and this gives us a very important and interesting effect on performance. How will this look in memory? On the left side, you had the version that we saw in Chrome, which was animations that are scattered around the heap with interpolations that are scattered around the heap, and they have pointers between them. On the right side is the version that I showed you with the data-oriented design. You have those long arrays of homogeneous types of the type that we are trying to animate. Again, they can be somewhere in the heap, but we get an order of magnitude better performance because we get an order of magnitude less cache misses. Because when we iterate over these vectors, we iterate over these long arrays. And we are no longer, our complexity of our ON, is the N here of the cache misses, is no longer the number of animations that we have, but is the number of different types that we're animating. And those are very, very few. We usually have 2 or 3 types per page that are changing. So they are usually positions and colors and let's say opacity, so a number. But even if you have 3,000 animations, like we saw in the demo, in the case of object-oriented programming that we saw, you usually have an 3000 magnitude of cache misses. But in this case, if we are just iterating over one type of animated property, which was our case, we'll just have one. And in C++, you can do it very elegantly. Your code can look great because you can have a templated method within your implementation that will make the code look good. So we want to avoid also branches. We saw that the object-oriented code was very branchy. And the most important, I'm sorry, the most important branch that we had was, is the animation active or inactive? You can do that very easily, obviously. You can have a Boolean if is active. If is active, you do something. Otherwise, you don't do anything in your update method. But that has all the problems with branch mispredictions and so on. So we can do, again, something very simple. We can separate our objects according to their state. We can have two arrays, one array for the active, one for the inactive animations. And now the operation of activating an animation is just moving that data, that animation state, from one array to the other, or vice versa. And now, when we go over the tick of our animation, we know we're going over only active animations. The details on this slide are not important. The code is not important. But if you look closely, the important thing that you immediately notice is that there are no branches. It works very, very efficiently. So how do we add an API with this? Unfortunately, an important part is a bit cut off, but I'll explain it here in the slide. It's not visible to you, but we want to allow the user to modify the animations. And obviously, the user shouldn't know about how to modify the different properties within the state to achieve its goal, like, for instance, stopping or changing the playback rate of our animation. We would like to give him a good interface. And object-oriented programming interfaces are great for that. So we create now a simple class struct, a simple class called animation or a struct called animation with the methods that we want to have. It's play, pause, stop, and so on. But it delegates all the actual modification of the data to the animation controller. And here what is not visible, because the slide is a bit cut off, is that it has just one piece of data. There's an animation ID, which is just a dumb handle that the animation object has, and it's used as an identifier from the controller to know what data to modify. And this decouples again the lifetime of our operations, because it's no longer a pointer, it's just a simple ID. And the DOM API in the controller is very simple. It takes the ID and does whatever it needs to do. So I'll skip on this. It's the comparison of the concepts that we used, but I'll skip it. We already talked about that. So the key points of data-oriented design that we implemented in this system were to try and keep our data flat, to maximize our cache usage. We used existence-based predication. This was the active-inactive stuff. We used ID-based handles to avoid lifetime issues. And we use this in table-based output. This is very important. Just the arrays that the other systems down the line will be using to implement their functionality. So I will quickly go over another system, actually, because this is an example that maps very well to data-oriented design, because you have these contiguous and fairly independent from one another animations. But what about another system that is more complex? And this is the system of style solving. Again, the details of how it works are not important. I'll just highlight the problem so that you can think in your head and probably map it to some problem that you have. The style solving is a system that assigns styles basically to every element. And the styles are the color, the position, and so on. And there is a fairly simple algorithm to do it. So it's simple in theory. It's very complex in practice. But you have matched a bunch of styles. So there are some styles that want to be applied on that element. Each of those has a specificity, which is how important it is. And you want to combine those and put them as the new values of your element. So it is fairly simple in principle. However, practically, it's not that simple because you have some constraints. The styles of the children depend on the styles of the parents. So you have a tree, and you have to traverse it in a specific way. Also, the elements you're applying this, so the nodes, so the node is a type in our system, in our object model, and the element inherits from it. So they're fairly interchangeable. The nodes in our system are big objects. So if we do that for everyone, we're accessing a lot of data that we won't be using, so it's a performance penalty. So the simplest way to do it, and actually close to the way it's done in Chromium, is to start from the root of your tree, look if an element or some of its children have changed, and decide if to go left, to go right, or to go both ways, to apply the style rules to every child. And going from the root down, you know that if an element upper in the tree has to be modified, when it's modified, its children, when they are modified and take the data from it, we'll get the latest data. So the order is very important. But now we're walking a tree. And walking a tree is very slow because all those elements are somewhere on the heap. They're huge elements and so on. There's also another important fact that we know from our domain knowledge is that, as we said, elements inherit nodes, but they actually have different rules for style solving. You can do a cheaper style solve on nodes. So these are all the elements that derive directly from node, but not from element. So the issues with the top-down algorithm obviously requires for you to know that your children have been changed, so that you know which paths in the tree to take. And this was why they were doing that set-neat style recalc that goes up the tree, so that the tree, the parents know that something has changed down the line. When you do the style solving, know where to go. And we have all these performance penalties. So let's try the data-oriented design approach. We have different types of input now. We have the list from our animation system, let's say, or from other systems, of the nodes that we know might have changed. Something might have changed there, so we have to recalculate their styles. We can split the algorithm in 3 phases. The first is to gather all the children of the elements that might have changed and sort them by their level in the tree. And we need to do that because if the parent has changed, it might change the child. So we have to restyle not only the parent, but its children as well. So we have to gather those children. And we have to sort them because we have to do it in the right order. We have to first style the parents, then the children. In the second phase, we can compute the styles of those sorted elements. This is the gist of the algorithm, how it works, how it will decide what to apply. It's not that important for us. And finally, we have to compute some final output. And obviously, one part of the output is the new values of the properties of our elements, but we also want some metadata. We want to know which nodes have been shown, which ones have been hidden, so that we can stop rendering them or something else. And let's see how those phases could be implemented efficiently. So let's decide for each phase the input, the output, and what additional data is needed from each node to implement those operations. So the first one was to gather children and sort them. We have the input, which is the list of nodes that might have changed. The output, which is a sorted list of elements, and the list of nodes. I mentioned that they, when you change the nodes, they can be done faster. And we know that the nodes are always leaves in our tree. So if we go first on the elements and then on the nodes, we're on the safe side. We don't have to sort between them. And we use just 3 pieces of data to gather all this information. We have to know if a node is an element, so in which array to put it. We have to know the children of each element. And we have to know the DOM level so that we can sort these arrays. And there's a pseudo algorithm which is extremely simple. The next phase, we have the input now is the output from the first one, which is the list of elements sorted by DOM level and the nodes. We have as output the new computed values, the most important output, but also some metadata which tells us what type of change we have applied. Is the element now shown? Is it hidden? Is it a transformation change? Is it a color change? This is important for other systems within our software. And the additional data that we'll need will be what styles might have changed, the list of styles that we have to match, and the type classification of each style. So if I'm changing the opacity, I know this is a visual change, a rendering change. And the third phase is just a classification phase. We take those the type of change and we put the elements, the pointers to the elements in different arrays so that we can again use this meta information somewhere down the line in our code. So the most important thing that we have to notice now that we have separated the algorithm in this way is that the different phases of our algorithm have different inputs, different outputs, but also different additional data that they need. So if all these data, this additional data that we need is in one object, we'll be having, we might be trashing our cache. It might not be the best way to do it because during phase one, we use a bunch of data from some elements, but other elements come in and clear that data. In phase two, we'll go over some of the same elements, but their data might be already evicted because we're using a lot of data. We would like to use less data in the different phases or less or better organized data in order to do the best we can with our caches. So there's an idea. It's not new. It's used in games. It's the so-called entity component system. So we basically call our nodes or elements entities, and they are made up of a bunch of components, which is just data. And conceptually, this will look like this. In object-oriented programming, all the data that we need is in the node. We use it wherever needed. But in data-oriented design, we can try and separate the node in three or multiple components. We have the hierarchy, which in our example was used in phase one. We have the styling, which in our example we used in phase two, and a bunch of others that might be used in other systems in our software. And as we have separated this in these components, now we can do a lot of clever things, like, for instance, allocate all our components in contiguous arrays and make the best of our caches. Okay, so let's analyze the results. And here the analysis will be between the object-oriented case and the data-oriented case for the animation system, just because it's a bit easier to reason about. So the performance analysis. This is a performance analysis on my PC, which is an Intel i7 with a lot of cache. So if you go for a machine that has less cache, the results are better, even better. But we're already 6 times faster. So the animation system that we design with data-oriented design is running 6 times faster, which is, it's not like 10% or 30%. It's significantly faster. But we didn't change, note that, we didn't change the algorithm. We didn't invent a new amazing data structure. We did that just by reordering the data and knowing how our machine will best make use of it. So think a bit about your code bases. There might be places where just by modifying your how you access the data or how you consume the data or how you have ordered and laid out your data, you might get amazing performance improvements. Next up is an interesting part, and it's scalability. And here by scalability, I just mean having this work on multiple threads. We're in the world of desktop computers, not distributed systems. So scalability here is, can we make this animation system work on more threads? our computers and phones have a lot of cores. We would like to use that. Well, in the object-oriented case, it would be somewhat difficult. We saw that there is a lot of coupling between the systems. So as I'm calling some methods, I have to check if they are thread safe. I have to make them thread safe if they are not. And I have to take care of a lot of data race conditions that might arise. There is also a bit of a problem with scheduling. We noted that some animations had that if not timeline return, so they won't be doing anything. And we would like our cores to be roughly equally busy, so that none of them is waiting and doing nothing. But you might end up with a lot of animations on core 1 actually being inactive and immediately returning, and core 2 is out of luck. It has a lot of active animations, so you might get this different distribution of workloads, and it's very difficult for you to control it in that case. With data-oriented design, we seem to be in a better place, because all our animation states and definitions are completely independent of one another. And we also know that when we iterate over the active animations, they're all active. So they'll be doing roughly the same amount of work. And we can do a very simple fork and join operation. We have a bunch of states. We can send, let's say, a third to core 1, a third to core 2, and the third part to core 3. And they do the animation logic. Each of one of them outputs its own array. And in the end, we can just merge the arrays. Extremely simple and efficient. So the testability. Testing these systems, again, in the object-oriented case, it's a bit involved. If you use unit testing or some kind of mocking, you have to mock a lot of systems just to test your animation system, because it goes and reaches out to all those other parts in your code base. With the data-oriented case that we designed, it was easier. You have a very well-specified input, a very well-specified output, and as long as the input is produces the output that you expect, the system is probably working fine. And you can also test it in a very controlled environment without reaching out to other systems. Now the modifiability is very interesting, because here it's a bit of a double-edged sword. In object-oriented programming, doing some quick modifications is very easy. So let's say that the requirements change. You have to do a very quick modification. So let's say if something happens, don't play the animation. This is easy. You add a boolean, and you have if this, do that, else do the other thing. If you want to keep the purity of your data-oriented design, that's a lot more difficult, because now you have to think how to separate that data. You have to think if you want to put it in another array, and so on. So those quick modifications are difficult in data-oriented design. But down the line, very often object-oriented programming styles of designs end up with those very complicated states, with those very complicated inheritance hierarchies that we saw in the beginning. So you have to be very careful. But here it's a bit of, if you take your time and really keep your data-oriented design pure, you in the end have a better time, obviously. But that can be true for object-oriented programming as well. So data-oriented design is not a magic wand. It has some downsides. The correct data separation can be very hard. And here comes some domain knowledge. So we had the luck to know our domain very well, to have worked for a very long time there, and know what exactly we needed from our systems and how they were going to work. If you don't know that, you might stumble upon some problems that you didn't expect in the beginning. Existence-based predications is not always very easy, and it's not always feasible if you have a lot of those states. But I believe that if you have a lot of those, you probably have some other deeper problem, and you can try and rework the logic or rework your rules to reduce them. The quick modifications can be tough, as I mentioned, and you might have to unlearn a thing or two. So this object-oriented type of thinking is very much ingrained in all of us, from countless books, from university and so on. And starting to think in this new framework can take some time, but it really pays off in the end, especially if you're looking for performance, if you're looking for simplicity in many cases. And unfortunately, the language is not always your friend. I work exclusively on C++ for this software. C++ makes it not so easy to do some of the things I mentioned, and other languages obviously make it a lot more difficult, even impossible in some aspects. But even in those languages, if you think about this, you get a long way. And when do we object-oriented program? Well, sometimes we have no choice. I mean, you can have third-party libraries that use object-oriented programming, so you have to adapt, you have to use that. You might have some requirements for your API. And I believe that polymorphism and inheritance, and interfaces mostly, definitely have their places in our code bases, but they are usually in the high-level systems, not, as we saw, in a very low-level system, in the system just for interpolating thousands of animations, where you have to pay an extremely high cost for this dynamic polymorphism. So C++ has great facilities for static polymorphism, so use that. Of course, make sure you don't explode your build times. It can be done. You can hide the implementations in files and so on. You don't have to have those templates spill out to all your code base. Be careful with that. And I want to finish with a couple of words that object-oriented programming is not a silver bullet. So keep in mind that data-oriented programming is neither. And to design great software, the best way is to use your judgment. And please do, because we need great software. Thank you.
We still have like roughly 3 minutes for Q&As. I can see your hand raised in here.
You said that C++ sometimes makes it hard to do this.
Yeah.
What would be your favorite language for doing this? Or your ideal language, I guess.
Well, I'm not sure there is an ideal language. So C++ is my favorite language because I work very actively in it, and there are some ideas on how to improve to make these things easier. There is actually an experimental language by a guy named Jonathan Blow, who's actually trying to design a language with all these ideas. And he's doing a very interesting job. It's still, he's creating a game with it, and his company is creating a game with it. So you can go and look for it. I don't remember the name of the language itself, unfortunately. But if you look Jonathan Blow, he has videos, he has it working.
JII, I've heard.
Yeah, something like that.
More questions? Over there.
Yeah, hi. I'm curious about the bit with the keyframes. Because you said that at compile time, you know how many of these types you have.
Yeah.
I'm here.
Yeah.
So how do you know that? Is that a usage-specific thing, or is that a general thing?
Yes. In our case, it is a usage-specific thing.
Okay.
If you don't know the types that you have, or there are too many, or you cannot really enumerate them, you are now in the world of dynamic polymorphism. Like, for instance, you support some plugin or something like that. But as we know which one of those we have, we can do that. And in the real world, like I believe 95% of the time you know the types that you're going to have. And like 95% of the inheritance hierarchies and abstract interfaces that I see in a lot of open source code, in a lot of production code, are just there so that once in the future we might have something there that is not known, but it's like 10 years later and no such types have appeared. So if this is your case, just go for the static types and don't bother, in my opinion.
Okay, thanks.
Hi. Sorry, here.
Hi.
Have you used aliasing SharePointer as some sort of poor man's, way of hiding simple objects in like continuous blocks, so the user doesn't really know it's in like continuous memory?
No. However, we usually try to use just those handles that hide everything, which was the case with the animation system. In the case of the component system, which is more complicated, we actually try to hide in some ways to the user that they are in arrays. And we do it in, unfortunately, an extremely complicated way, just because of the way C++ works. But it's for a whole other talk.
I believe we have time for one final question, and the rest will have to be taken offline.
Hi, thanks for the talk.
Hi. Thanks.
I kind of find it interesting that the splitting of complex classes is similar to me to single responsibility principle. Could you comment on that?
Yes, it is similar to single responsibility principle. And the single responsibility principle is obviously extremely important. And we were able, I believe, to achieve it with the data-oriented design way, especially for the examples that I showed, better than the object-oriented code base. Although, in theory, it's the most important thing in object-oriented programming and so on. But very often, due to the way the real world works or companies work and so on, you end up with this smudged single responsibility, because single responsibility, I believe, is exactly this. So to use the parts that you need in the parts that where you need them, and not this, I have the car, which is the object, and it's its single responsibility to do everything that a car does. And it's described in books as well, but in the real world, you don't see it that much. So if you think in the framework of data-oriented design, I believe it's just easier for you to reach that thing. But it's the same thing.